All right, everyone. My name is Prathap Ramamurthy, and I'm a professor at the City College of New York in New York. This work was done by me and my past student, Gabriel. We're going to basically look into some boundary layer observations, really look into what's happening during heat waves in the urban boundary layer. One of the main motivation. Yeah, for the work is heat waves, as predicted by IPCC, kind of like increasing in intensity and frequency in this last year in July 2023, hottest year ever recorded. But one of the interesting things is there's been a lot of focus on the heat waves, quite a lot of studies, mostly focused on the surface layer, particularly the urban surface layer, looking at like urban rural differences and some of the heat wave dynamics. However, the impact on what's happening in the mixed layer, particularly, is really missing. So for this work, we really wanted to focus on what's happening in the urban mixed layer, particularly with the mean characteristics, like what's happening to the temperature field, what's happening to the wind field, and also what's happening to the turbulence in general in the urban mixed layer. And we could see, it's very interesting to see, so many presentations, particularly in this session, which really focused on the mixed layer dynamics quite a bit. But this is one of the biggest significant knowledge gaps in urban boundary layer research, where majority of our understanding and majority of the studies are really focused on the surface layer. And also, our model's ability currently, particularly for high pressure heat wave situations, they do pretty well getting the near surface temperature. But however, we really don't know about how well they perform in understanding or getting the mixed layer dynamics. And that's one of the main focus of this work. And also as we move on, right, we're going to be focusing more on hydrology, air quality. And for those issues, the boundary layer dynamics becomes extremely important. So this work is focused in New York City. So, New York City has like 5 boroughs, the Manhattan, the Bronx, Queens, Brooklyn, and Staten Island. So for this particular work, we're going to use the data from these 4 stations. SI Staten Island, CC is technically in Upper Manhattan area, and then BX is the Bronx side and QS is the Queens side. So almost all these sites have a wind lidar, and then they also have a microradiometer, ceilometer, and most of them are also coupled with a surface flux station in general. The city, oops. So New York in general. So on the right hand side, you can see a map which is like divided all the different zip codes or pin codes in New York area, and it also tells you like what the average building height in all these different zip codes are. And then the image here kind of gives you an understanding of vegetation and build cover in the city. So these are like measurements that are available for public in general. New York City does this like once every 5 6 years. They produce a map which is about 3 feet resolution. One of the good things is many people think that New York City is like extremely dense and very tall buildings, which is true, but that's mostly in Manhattan area. But when you move into the other outer boroughs in general, it's pretty different in general. In fact, if you go to places in Queens and Staten Island, there's a lot of places. A lot of areas have a very high vegetative cover in general. So you kind of have representation for all different local climate zones. Another thing that's very important about New York, understand the climatology of New York is like it's surrounded by water. So we have the Atlantic Ocean towards the east, but there's also a pretty big river called the Hudson River on the west side. And then you have the East River or the Long Island Sound in the middle of it. So it's extremely impacted by all these waterways in general. So the first thing I want to just show you is kind of like what the difference in temperature and humidity feel in all these 3 sites. We picked the top one is Bronx, and then Queens, and then Staten Island. And then you see it for three different time periods, like 6 o'clock local time, 12 local time, and 18 local time. I do just tell you, like, here we use data from a microwave radiometer, which is like, we've been testing this along with radiosondes in Houston, where we find like the values are not completely right, but however, the microwave radiometer is able to produce the difference between like what's happening in like a heat wave day or the regular day. So it's an okay thing to see like the difference in the thermal and the thermal field particularly, and also the water vapor field. But however, I do tell you like the performance of the microwave radiometer for an urban area is pretty bad in general. We've been able to fly some radiosondes in Houston, and we have some good measurements to show like how bad it is. But in general, overall, from here we see like there's a huge difference in the thermal profile during a heat wave on a regular non-heat wave situation. So this has been averaged over a lot of data, so nearly like 3 years of data. In New York City, a heat wave in general is like any 3 consecutive days when the midday maximum reaches about 90 degrees Fahrenheit, so about 32.2 is considered as a heat wave category. For a lot of this work, what we did was like we took all the temperatures and then looked at whatever was above the 95th percentile. We consider that as an extreme heat event. But it clearly shows like throughout the entire city, there is difference in temperature like all through the boundary layer height for all these sites. And interestingly, the humidity field is also pretty high. Like, humidity during these heat waves are extremely high in the city, which has a lot of implications for near surface heat index. Now, when we move on to the wind field, these are LiDAR measurements. Surprisingly, very little difference in terms of how the wind behaves. This is just a zonal wind, three different sites: Bronx, Queens, on Staten Island for three different time periods again. The only major difference was in the very, very early morning period, you have this low-level jet that happens during non-heat wave periods. However, during these extreme heat wave periods, we lose that low-level jet in general. Apart from that, the momentum field is more or less pretty similar. So overall, so there is a significant difference with respect to the temperature and humidity field, but not that significant difference when we take whether the zonal wind or the vertical wind. Now let's move on to the turbulent intensity at the different heights. So here, this is just the Manhattan site, and we've divided it into different surface layer stability. So on the very left, you have a situation which is extremely or highly unstable, and then unstable, moderately unstable, neutral, stable, and highly stable. So one of the red lines here are from extreme heat periods, and then the blue lines are from normal periods. So one of the most important, interesting things you would notice is there's not much difference in the turbulent intensity at all these different heights during these extreme heat periods. In fact, the variability at each and every level is much reduced. If you look at the blue lines in general, the standard deviations are higher, like in the lower boundary layer. However, you don't see too much fluctuations during the heat wave period. And then what we did also is like we were doing some vertical scans, took data at almost like 1 hertz frequency, so we were able to do some decent power spectra. So here it's the vertical velocity spectra, again differentiated into these 5 different boxes: highly unstable, unstable, moderately unstable, neutral, stable, and highly stable. And they're all here normalized by the wind speed, square of the wind speed. So the interesting thing is like there are distinct layers. Like if you look at the moderately unstable period, -1, zeta -1 to -0.1, you can see there is kind of like a 2 distinct layer, one in the lower 700 meters, and then another distinct layer above that. But then as the boundary layer becomes very, very unstable, you could clearly see there is a pretty big difference in terms of the energy content at different levels. And then, as you would expect for a neutral level, the boundary layer pretty much collapses, whereas highly unstable turbulence is extremely intermittent in general. But the main point here is like the urban mixed layer is pretty heterogeneous. This is probably maybe due to a lot of internal boundary layer effects where your different layers are in different turbulent regions. And same if you look at some of the convective scaling, so here we've taken the variance of both the zonal wind and the vertical wind, and then used your your mixed layer similarity convective scaling. One thing we see is like for the zonal wind, particularly for the Queens and Staten Island side, which is less built up, there is some type of agreement with what we see in the literature. So those dotted lines you see are from Sorbjonne and Lenshaw, which are for more ideal surfaces. However, for Manhattan's side, very little correlation or with what we observe in the literature. And then final thing that I want to kind of talk about is there's been a lot of debate about like what happens during the interaction between sea breeze and heat waves. In some of the earlier modeling work that we did, we found that during these heat wave periods, we lose the ability, the cooling ability due to sea breeze, and that creates a lot of situation. But interestingly, what we found out is like there are some heat wave periods where you actually have sea breeze. So in this case, you have a ridge formation in the Atlantic, so you still have a strong sea breeze. Whereas in some cases, when the anticyclonic system occurs in the continental part, then you kind of lose the sea breeze. And what we see is like here on the top case is without sea breeze, and the bottom case is with sea breeze. Interestingly, the wind speeds were much higher during the without sea breeze case when we have the land breeze system. But however, for the sea breeze system during the nighttime and early morning period, there is a lot more cooling. However, during the midday period around 1500 local time, there is very little difference. So during the peak hour period, not much of a difference, but then in the nighttime and evening periods, the sea breeze does have a pretty significant cooling effect. And that's what this kind of highlights to in general, where with the red lines here show the case one where no sea breezes, so you do see like high temperatures throughout the boundary layer, relatively high temperature throughout the boundary layer, all the different sites. But however, the wind speeds were much higher during the land breeze time. And with that, I will stop. All right, thank you so much. Thank you.
All right, we have time for a question from the audience. Yes.
Thank you very much for your interesting talk. I have a question relating to your TKE profile there. Actually, I'm kind of expecting a high TKE in the extreme heat, especially the wind speed is kind of the same for when you compare normal, because like more.
Okay, we didn't really measure TKE. All right, we only used like one LiDAR. It's very hard to measure TKE with just one single LiDAR. You kind of need to use two of them, use a plane, map the planar field, 2D field, in order to get an understanding of all three fluctuating components. All right, so here we are mostly for some of the spectral stuff, we use a vertical stare. And if we want to do the radial, and otherwise we have to get the radial one. So we can't really do TKE with just one LiDAR, or at least we didn't do that.
That's all. Actually, I totally agree with you that the flow inside urban canopy is really important. But I found these days maybe people more care about the higher layer, such as above the roughness layer. But usually we model the roughness layer, especially inside the urban canopy layer.
Mm-hmm.
We found that actually the flow will directly affected by the buildings.
Yeah.
So in your experiments, how you think about what's your consideration about the geometrical effect? And also, can you give me some experience about the link between the temperature and wind flow field?
Okay.
Usually we model just the wind flow field, but recently I think about add some temperature, but I don't know the boundary layer of the boundary layer of the velocity and the boundary layer of the temperature.
The thermal
difference between each other.
So for all our cases, right, we actually did not care a lot about the urban canopy layer. So all our instrumentation for this particular work was placed on top of a building in general, the lidars and so on. So we did not really care too much about the canopy layer. But however, my guess would be like, depending on, one of the things we notice is like whenever in New York, for example, you're in an area where there is a lot of variability in building height, there is a pretty big fluctuation in the pressure field, so that gives rise to like a lot of high velocity. Whereas on the other hand, if you're in an area where the building sizes are heights are much more uniform, you do not have the same fluctuation in the velocity field.
Very good. Please join me once again in thanking Professor Mahmoud. Very good in this session about geographical representation.